Good day everyone. Welcome to Unit 4, Lecture 4 for CpE2301 Logic Circuits and Design. Unit 4, Lecture 4 covers flip-flop excitation tables and how they can be used in the design of sequential circuits. Before we go to the discussion of the flip-flop excitation tables, let us first recall the flip-flop characteristic tables discussed in Unit 4, Lecture 2. The tables shown here are the flip-flop characteristic tables. From previous discussions, we have learned how these tables show the behavior of the JK, SR or RS flip-flop, D, and T flip-flops. These characteristic tables show us that if we know the inputs to a flip-flop, we would be able to know its corresponding behavior with regards to its next state. In a JK flip-flop, for example, if we know these J, K inputs, we would know the next state of the flip-flop as shown by Q T plus 1 and described by the state here. In an SR flip-flop, if we know these S and R inputs, we would know the next state of the SR flip-flop as shown by QT plus 1 and described by the state here. The same goes for the rest of the other flip-flops. What this means is the characteristic tables show the behavior of the flip-flops based on our knowledge of the inputs. And when we know the inputs, we can later identify the corresponding behavior of the flip-flop with regards to its next state. However, in some or most cases in design of logic circuits, we have to consider the output or the behavior of the circuit first, then identify later the corresponding inputs needed so that the circuit will behave in the manner we want it to behave. This is what we want this time for the flip-flops. This is now where the flip-flop excitation tables come in. So here we have the flip-flop excitation tables for the 4 flip-flops. This for the RS or SR flip-flop. This is for the JK flip-flop. This is for the D flip-flop. And this is for the T flip-flop. When you look at the flip-flop excitation table, you will see the transition values from one state to the next state and the corresponding flip-flop inputs needed for that transition to occur. Let's look at the excitation table for the RS flip-flop. On this column, we can see the present state of the flip-flop, which is QT. On this column is the next state, which is QT plus 1. And here are the S and R inputs for the transition from the present state to the next state to occur. For example, if the flip-flop state or the value it is currently holding is 0 and we want it to go back to the same state 0 for its next state, we can see that we should provide an input of 0 and X for S and R respectively, so that that transition would occur. An X input means don't care, so it does not matter what the input value for that case is. Here, if the flip-flop state or the current value it is holding is 0, and we want it to go to a 1 state for its next state, we can see that we should provide an input of 1 and 0 for S and R respectively, so that transition would occur. For present state to next state transition of 1 to 0, we should provide an input of 0 and 1 for the S and R inputs respectively. For present state to next state transition of 1 to 1, we should provide an input of X and 0 for S and R respectively. The rest of the other flip-flop excitation tables will show you the same information for each particular flip-flop. Here for the JK flip-flop, we can see the present state to next state transition and the J and K inputs needed for those transitions to occur. Here for the D flip-flop, we can see the present state to next state transitions and the D input needed for the transition to occur. For the T flip-flop, we have here the present state to next state transitions and the T input needed for those transitions to occur. Let us now try to use the flip-flop excitation tables to solve an example problem. So here we have the design problem. It says, design a logic circuit that performs the state transitions shown in the state diagram below. Use JK flip-flops. So here we have the state diagram of the circuit. In the state diagram, we can see that these are the 4 states: 1, 2, 3, and 4. In order to cover the 4 states, 2 flip-flops are needed so we can have 4 combinations for the state values of the 2 flip-flops, as seen here with the 2 digits or 2 bits on the states. As mentioned in the problem statement, JK flip-flops should be used for the circuit. These values in red represent the single circuit input value needed by the circuit so that the transitions, shown by the arrows, from one state to another would occur. Take note that this input is an external input to the circuit and not the actual flip-flop inputs to the 2 flip-flops. The input to the flip-flops shall be determined later as we progress in the solution. Take note as well that there is no output specified for the circuit. So based on the state diagram, we can come up with a state table for the circuit, and it looks like this. Based on the information we have from the state diagram, these are all the present state and input combinations for the 2 flip-flops we name here as flip-flop A and flip-flop B, and the single input we name as X. These present state and input combinations will result to these next states here as described by A t plus 1 and B T plus 1. Just like what we have seen from the state diagram, we can see here that if these are the input values, the two flip-flops A and B will transition from these present states to these next states. The question now is, how do we make flip-flops A and B perform those transitions? Now let's remember that the state of a flip-flop corresponds to its output Q. This means that when we know the present state to next state transition of a flip-flop, that is the same as knowing its Q to QT plus 1 transition. All we have to do now is identify the flip-flop inputs needed for the transitions to happen. This is now where we make use of the flip-flop excitation tables. As said in the problem, we shall be using JK flip-flops. Using the JK flip-flop excitation table, we can identify the needed JK inputs for flip-flop A so it can transition from its present state to its next state. Using the JK flip-flop excitation table, we can now have these JK inputs for flip-flop A. As seen here, for the first state transition, present to next, in the state table, we want flip-flop A to transition from 0 present state to 0 next state. So looking at the excitation table, for a 0 present state to a 0 next state transition to occur, we need a 0 and X inputs for J and K inputs of flip-flop A. That is why we have 0 and X here for JA and KA. The same goes for the next transition here. We have 0 present state and 0 next state. So that's why we have 0 for JA and 0 for KA. Next, we want flip-flop A to transition from 0 present state to 1 next state. So looking at the excitation table, for a 0 present state to a 1 next state transition to occur, we need a 1 and X inputs for J and K inputs of flip-flop A. That is why we have 1 and X here for JA and KA. So by repeating the same steps, you can identify the needed J and K inputs for flip-flop A for the rest of the state transitions. After that, you can proceed to doing the same for flip-flop B. So here we already have our J, B, and KB inputs for flip-flop B. The next thing that we have to do is to obtain the Boolean functions for each of the flip-flop inputs so we can translate them into an actual circuit later. We can perform the K-map method for each of the flip-flop inputs using the present states of the flip-flop A and the present state of flip-flop B together with the input X. And so we have this. Here we can see that by using the present states of A and B and the input X and the values for the JA flip-flop input, we can derive the Boolean function for JA. And here we are using again the K-map method. The function for JA is bx prime as described by this min term and don't care condition in a group in the K-map. The circuit equivalent of this function will serve as the input to the J input of flip-flop A in the circuit later. You can do the same process for KA, JB, and KB to obtain their Boolean functions. Once all the Boolean functions are obtained, you are now ready to construct the circuit based on the derived Boolean functions. The circuit will now look like this. Here we have the two JK flip-flops, A and B. Their J and K inputs are based on the Boolean functions we derived from using the K-map method. Here, for example, for the JA input, we were able to obtain JA is equal to B x prime earlier. That is why we have B and x prime for the JA input. We simply do the same for the KA, JB, and KB inputs. Of course, let's not forget about the required clock pulse inputs to the flip-flops coming from a clock generator. And also remember that these flip-flop outputs are not actual circuit outputs. They are simply internal circuit outputs of the flip-flop components. They are just highlighted here for this discussion. Let's now try to see how the solution goes if another type of flip-flop was used. Because in actual applications, you can use any of the 4 flip-flops to implement the solution. That means an RS or D or T flip-flop can be used for this implementation. Let's try to use a D flip-flop to solve the same problem. Let's go straight away to the state table. At this point, we now need to identify the D input for flip-flop A. Using the excitation table for a D flip-flop, we can obtain the flip-flop input DA, which are the inputs needed for the transition of the present state of flip-flop A to its next state. The same is done to obtain DB, which are the inputs needed for the flip-flop B for the transition from its present state to its next state to occur. As you can see, we have lesser flip-flop inputs to identify since we are using a D flip-flop this time, which only has one input compared to what we used earlier, which is a JK flip-flop that has two inputs. This would also mean that we have lesser K-map solutions to perform later. So now let's obtain the Boolean functions for the flip-flop inputs DA and DB using the K-map method. Here, using the K-map method and using the present states A, B, and input X, and the values for the DA and DB flip-flop inputs, we are able to obtain the flip-flop input functions for DA and DB. We then translate these functions into their equivalent circuits. The circuit will now look like this. Here we have the two D flip-flops, A and B. Their D inputs are based on the Boolean functions we derived from using the K-map method. Here, for example, for DA, we were able to obtain DA is equal to AB prime or BX prime earlier. That is why we have A and B prime, or with B and X prime for the DA input. Here, take note that we do not need an inverter or NOT gate to obtain B prime from flip-flop B. We simply took B prime from the Q prime output of flip-flop B. To complete the circuit, you simply do the same process for the DB input. Again, do not forget about the required clock pulse inputs to the flip-flops coming from a clock generator. Also remember as well that these flip-flop outputs are not actual circuit outputs. They are simply internal circuit outputs of the flip-flop components. They're just highlighted here for this discussion. So if you want to try out using the RS and T flip-flops, you may also do so. So that ends this lecture. Thank you for watching and listening, and have a good day.